for halogen-free flame retardant compositions. These flame retardant compositions generally we talk in polymers. So as we know, polymers have become the indispensable part of our daily life, whether it is textile, plastic containers, wiring, automotive parts, packaging material, anything. And these polymers are made up of long chain carbon compounds which are highly flammable. And that's why in case of fire, these polymers, they catch fire very rapidly and it leads to the severe damage to the lives and the properties. The data shows, NCRB data shows that in India, every day, around 60 people die due to fire accident. And in a year, around 25,000. Among these, around 2/3 are women. If we talk about in the terms of the property loss, around rupees 1,000 crores are lost every year in India due to fire. 2020 data says that these are the 5 topmost states in India: Madhya Pradesh, Odisha, Chhattisgarh, Maharashtra, and Tamil Nadu, which witnessed the maximum number of fire accidents, and it accounted for around 54.7% of total fire-related casualties in India. In 2021, around 1.6 million fire accidents happened, in which 27,027 lives were lost. So it's a huge data which makes us to think of, can we do something to prevent this much loss of lives and properties? So yes, the answer is flame retardant. Before coming to the flame retardant, we can understand why the fire happened. For the fire to take place, 3 components are necessary. They are mandatory: oxygen, heat, and fuel. It means if any of the component is missing, then fire will not take place. And this makes the basis of the flame retardants to work on. So these flame retardants will either remove oxygen, or they will reduce the heat, or they will prevent the fuel to come in direct contact of the fire. So what are the flame retardants? These are the compounds, chemical compounds, which are either compounded with the polymer, or it is applied on the surface of the polymer to prevent the direct contact with oxygen. So these flame retardants, they prevent some of the flame retardants.
Excuse me, ma'am.
They reduce the...
Sorry to interrupt you, ma'am. Are you changing the slides in your presentation? Because what we can see is only your first slide.
Yes, sir. I'm changing. I do it again if it is not visible.
Now it is. Yeah, now it is getting changed. Yeah. Please.
Okay, so I will keep it like this.
Can you please put up the entire presentation on the presentation mode?
Sir, slide show, fine.
Sure, sure. Yeah. That will be easy for the audience to view properly.
Yeah. So shall I come to the second slide again?
No, you can continue from the third, because most of
Yeah. So some of the flame retardant.
To the presentation mode, ma'am. The slide show you.
The third slide is not visible.
It will just enlarge the visibility.
Okay, it's visible now.
Audience, I would like to have a word from the audience. Are you all able to see clearly?
Well, it's not full screen yet.
Okay, ma'am, please can you switch to the full screen?
It is full screen from my side.
Just change 1 or 2 slides, like next and back.
Yeah,
maybe that will...
Fifth slide.
No, we are still seeing the flame retardant slide. Nothing is changing.
Okay.
The mouse is operating. But
so I will
changing on the screen.
It's changing now.
Yeah, it's changing now.
Okay, ma'am.
So every time I will put it in on the full screen. Every slide I will come to, and I will put it on the full screen. This flame retardants is visible, right?
Sure. Yeah. Go ahead.
Yeah. So these flame retardants, they remove any of the 3 components from the surrounding, either oxygen, or they reduce heat, or they prevent the fuel. And this makes the basis of the working of the flame retardants. Like some flame retardants, they reduce heat by liberating water. Some make the char layer over the polymer surface. So they prevent the polymer to come in direct contact with the heat, and some liberate out non-combustible gases. So oxygen concentration is reduced, so the flammability is reduced. Now, in case of fire accident, what happens when fire take place? Uh, it spreads very fast. So the people who get stuck there, they get a very little time to come out. And generally, this escape time is only 5 minutes. But when we use flame retardants with the polymer, this escape time can be increased to 15 minutes. And since in these fire accidents, every second matters, so the people get sufficient time to come out of the accident place and can save their lives. Is it visible? The next slide.
Yes, ma'am, please go ahead.
Yeah. So the flame retardants, they generally refer to a function, not the particular class of the compound. Function means their work is to just prevent the spreading of the fire. Many compounds can work as flame retardants, like metal hydroxide containing flame retardants are there, nitrogen containing, boron containing, phosphorus containing, and halogen containing. If we talk about these different categories, among these, halogen containing flame retardants were the most important due to their high efficiency. But the problem is halogen containing flame retardants are highly polluting. And when they are heated at high temperature, they they take out the toxic gases, which contains dioxins and furans. These dioxins and furans, they enter the body, damage our immune system, and cause lung cancer. And its traces have been found in human blood and breast milk also. So all the countries, European Union and India has also taken steps to eliminate most of the halogen-related flame retardants from the applications. It means since the halogen-related flame retardants have been eliminated out, it means we have to now work on the development of non-halogenated flame retardants. Now, since it's a function, it's not a particular category, so the performance has been discussed, or performance are checked on the basis of certain parameters, which include UL94, limiting oxygen index, that is LOI, heat release rate, total heat release, and smoke density. Among these, for the industrial point of view, UL94 is the most important test, which is a vertical burning test. In these three ratings are there, V0, V1, and V2. If the burning stops, in this we keep the polymer in the vertical state and we burn it with butane. And if the burning stops within 10 seconds and no dripping takes place, then it passes the V0 specification. If burning stops within 60 seconds and no dripping is taking place, then V1. And if burning stops within 60 seconds, but dripping is also there, then it is V2. So our efforts are always to achieve V0 specifications. If we come to the flame retardant markets, globally, in 2022, the flame retardant market was of 7.6 billion USD, and which is expected to rise to 13.7 billion USD in 2032. It includes both halogenated and non-halogenated flame retardants. Now, since the government is pushing towards the use of the non-halogenated flame retardants, so in 2023, the market was of 5.64 billion USD for non-halogenated flame retardant, which is expected to rise to 12.2 billion USD by 2033. So it means we have the ample opportunity to develop to work in the field of the non-halogenated flame retardant and to find out the more efficient one. Was this slide visible to you earlier? I explained this.
Yes, ma'am. This is. Let me make a point over here. Only 6 minutes left, ma'am. So can you please?
Yeah, sure.
Yeah. Try to wind up your presentation.
Sure.
Within that. Yeah.
Now, one more thing is there with the flame retardant. Many flame retardants are being used, as I told you, nitrogen containing, phosphorus containing. But the drawback is when we use a single flame retardant in a polymer. So we need high loading. Around 40 to 60% of the flame retardant we need to add to bring that efficiency. It means if we can use some synergist, which can reduce the loading of flame retardant, then it is a big step in this direction. So we had worked on the development of the synergist for the flame retardant. We had developed graphitic carbon nitride from melamine. So it was pyrolyzed at high temperature, around 500 degrees centigrade. We heated it in the absence of oxygen. So it condensed and polymerized to graphitic carbon nitride. It has two-dimensional structure, more like of graphite, and the different layers are joined together by weak van der Waals forces. This is this is FTIR and XRD of the graphitic carbon nitride. We got the peak at 806, which corresponded to triazine units. And the peak which we received in the broadband of 3000 to 3400, that was due to some associated water and NH stretching. In XRD, we got the characteristic peak of GCN at 27.6 degree to theta, and it was well supported by the literature. Then this GCN we mixed with the polypropylene along with piperazine pyrophosphate. This piperazine pyrophosphate is used as a conventional flame retardant. But since it is used in high amount, so we wanted to use some synergist so as to reduce its concentration in polypropylene. So we had compounded it with the help of the extruder and with the help of the injection molding, we converted it into the specimen, which was tested. So here in the table, you can see the composition. NPP is the neat polypropylene, in which was a pure polypropylene. In PP naught, we added polypropylene, piperazine pyrophosphate 22 gram. In PP1, it was 18 gram. And in PP2, PP3, and PP4, along with the 3P, that is piperazine 3 pyrophosphate, we have added GCN 1 gram, 1.5 gram, and 2 gram. So when we did the UL94 test for these compositions, we found that only PP2 and PP3, in which GCN was added in 1 gram and 1.5 gram, they passed that rating. Then we performed the different flame retardant performance of the samples like LOI, heat release rate, total heat release, and smoke density. So you can see PP1 was that in which we have not added a GCN, and 3P amount was 18 gram. PP3 was in which GCN was added in 1.5 gram. So you can see LOI was increased by 15.8% in comparison to PP1. We need high oxygen to prevent the burning. So the LOI was increased. Heat release rate was decreased by 62.6%. Total heat release was reduced by 42.6%, and smoke density was reduced by 17.6%. But when these flame retardants are added, the mechanical properties also get affected. So we need to study the mechanical properties as well, because we need some standard properties. So here you can see the melt flow index. In comparison to PP1, it was increased by 20%. Tensile strength was same. Impact strength, it increased by 3.3%, and elongation at rate was increased by 6.7%. So it means we were getting better mechanical properties along with enhancing the flame retardant properties by the addition of 1.5 gram GCN in the sample. So here we can conclude that GCN has been used successfully for the as the synergist in the regular FR formulations. Another thing, we had done all the tests in polypropylene. Polypropylene used piperazine pyrophosphate in an amount around 30% amount. Whereas when we use magnesium dihydroxide in polypropylene, it is used in 60%. But when we are using GCN, it is used only in around 15%, and the better efficiency we are getting. Another synergist which is being used these days in polypropylene is graphene, but the drawback is graphene is black in color. So we get the product black, whereas our GCN was creamish in color, so we can use it in the different colored polymers as well. The results we received very encouraging, and so more and more work is open for the researchers to do in this direction, so that we can get the better and better non-halogenated flame retardants. These are my team members. Mr. Vinod Kumar Sharma, he's an industrialist and he's doing PhD with me. He's working on the same topic, flame retardants. Dr. Ashish Mathur, Dr. Sherry Singhal, and Dr. Shikha Wadhwa. They are in UPS Applied Science Cluster, and they are my team members. Thank you very much.
Thank you, sir, for giving me this opportunity to present my work here. My work is based on the detection of a skin lightening agent, Quinol, in whitening cream using electrochemically reduced graphene nanosheets, cobalt-doped graphitic carbon nitride modified electrodes. We have actually my work is basically based on the preparation of nanomaterials for the electrochemical sensing of different analytes. So for this work, we have detected the Quinol, which is also known as hydroquinone, and which is generally utilized to prevent melatonin production in the skin, leading towards the reduction of skin color tone. But its long-term use in cosmetics causes different kinds of the skin problems, kidney failures, and headaches. So basically, it is employed for other purposes also, like pharmaceutical, oil refineries, textile, dyes, and effluents from such manufacturing units causes serious concern to the environment and human health because of its slow degradation. That's why the real-time analysis is very necessary for this particular compound, and we have developed a particular electrochemical sensor by the development of a special nanomaterial. Basically, why we use electrochemical sensing? Because the electrochemical sensing is a very cost-effective method, ease of use, fast, and it can be modified in a form of a small device which can be portable. And while electrochemical sensing of analytes, basically when we try to design the nanomaterial so that can prevent the influence of other interferences which may be present in the real samples by lowering the overpotentials. So we have prepared the nanomaterial. This electrochemical setup we use, the 3 electrode system is there, in which this is working electrode, where basically we use the glassy carbon electrode on which we modify our nanomaterial. We make a thin film on the working electrode, that is glassy carbon electrode, and then we use the one reference electrode, which is invisible chloride electrode, and one counter electrode, that is platinum bar electrode, and three electrode system is there. And we take the sample here, in which we have to analyze the analyte, and then we connect it to the potentiostat, and it is totally based on software. A CHI instrument imported from USA we use here, and the technique we use for the sensing, that is cyclic voltammetry and differential pulse voltammetry, and this complete voltammetric cells are referred to as sensors.
Yeah, Dr. Manorama, may I request you to kindly change the slide?
Sir, it is changing.
Okay.
Sir, is it?
Can I have a word from you? Whether are you able to see any changes in the slides?
Sir, I'm showing the slide schematic representation of synthesis of nanocomposite. Is it is it displaying?
No, I think
We are
display
still seeing
slide
the
is the
first
first
slide.
one. First one, yeah.
Oh, okay. Sorry. Then
Yeah, now it is changed. Yeah.
Now it is?
Now it is, yeah. Go ahead.
It is visible now?
Yeah,
Yes.
visible.
Okay, sir. Now,
Yes, yes, please go ahead. Yeah.
this is a schematic representation of synthesis of nanocomposite. Is this slide?
Yes, yes, yes. Please go ahead.
Okay. So here we have prepared the nanomaterial. So we have taken the graphene. We have prepared the graphene nanosheet from the graphite rods, which are generally we have collected from the unused battery, ever-ready battery, and then these graphite rods were cleaned with the nitric acid, and then the both two graphitic electrodes rods were used as an electrode in the electrochemical cell. Here, one is cathode, one is anode, and here. When in the these two rods are dipped in a cysteine solution, which is a kind of amino acid, plus the cobalt doped graphite carbon nitride solution, and in both the combined electrolytes of this, when we put the two rods and we apply the current, then the graphene nanosheet is prepared by reducing the anodic graphitic rod, and because the cysteine solution is there, means cysteine molecules are there in the solution, and cobalt doped graphite carbon nitride is there. So this type of arrangement is actually we got here. This is graphene nanosheet, which is combined with the cysteine molecule, and then graphite carbon nitride is interacted with the graphene nanosheet, prepared graphene nanosheet with the pi-pi interaction. So totally non-covalent interactions are there, and this nanomaterial have been prepared, which has been further utilized for the electrochemical sensing of the Quinol. Further, we have characterized this prepared nanomaterial with the FTIR, Raman, and XRD. Through the Raman and XRD, we easily got that yes, there is a formation of the nanocomposite. Then further, we have studied with the XPS study. In the surface spectrum, we easily can see there is a different elements are present: sulfur from the cysteine molecule, nitrogen, graphite carbon nitride, carbon, oxygen, cobalt, all elements are present in surface spectrum. So further, we have studied with the carbon 1s, through which we can get okay, yes, there is a C double bond C, C double bond C, C single bond N, and in the N1s, the convoluted spectra of the XPS, we can easily got yes, there is a presence of CNC, which is in graphite carbon nitride, and CN 400.6. So these all are binding energies 399, which are the characteristic binding energy for a particular bondings. So that's why through which we can easily get yes, the formation of the nanocomposite have been done. Further, we have studied the morphological study with SEM with EDEX, and in the EDEX also we see here in the
Yeah, Dr. Manorama, sorry for the interruption. We are still stuck on the fourth slide. Can you please again change it?
Sir, how is it done actually?
I think there are some network issues. Never mind. Yeah, sure.
Okay.
We are on the SEM with EDEX. Yeah.
Okay, so I'm just zooming. I think slideshow I'm doing, so that's why problem is. Is it enough, sir, or shall I do slideshow more?
Let us continue with this currently.
Okay, so in the EDX spectra, you can see here the sulfur, carbon, nitrogen, oxygen. Oxygen is there, but when we dope with the graphite carbon nitride, cobalt doped graphite carbon nitride, so again all the elements are present which can be detected in the EDX spectra. Further, we have done with the TEM here. This is the graphene oxide TEM, which is showing the transparent morphology, but when it is combined with the cysteine molecule, then the black spots are there, which generally is showing that yes, cysteine molecules are there. Then further, it is have been combined with the cobalt doped graphite carbon nitride. So the figure E shows in the different phase lines, and here these are the C and F, the diffraction pattern, and F showing the diffraction pattern of the finally prepared composite, because in the C, diffraction pattern C, which is for only the graphene nanosheet, cysteine molecule modified graphene nanosheet. So here the diffraction pattern is like amorphous. It is showing the amorphous nature, but in the F figure, which can see that there is a fine crystalline lines are there. clear lines are there. So this showing that the material is now crystalline. So further we have done with the electrochemical studies and successfully we got that this material is very much electroactive.
Try putting this on the slideshow mode.
Okay, okay, sir. Okay, now it is okay, sir.
Now it is okay, but try putting it on the slideshow mode. Yeah. Because every time you have to be interrupted again.
Okay.
Otherwise.
So I'm not putting at the slideshow. I'm just continuing with this. Okay, sir.
Fine. Go ahead.
Okay. So with the material, when we modify on the classic carbon electrode and we have taken the cyclic voltammetry, cyclic voltammogram, then we have recorded this. Yes, the material is very much electroactive. When we increase the scan rate, so at the different scan current increases from 5 to 200 millivolt per second. Then we have decided that, okay, now we have to check whether the other isomers of the hydroquinone or quinol may interfere in the detection of the hydroquinone or not, like resorcinol and catechol. But we found that no, other isomers also gives the response, but they give the response at a different potential. So there will not be any kind of interference of other isomers. So further, we have studied with the different modified electrodes at each step. With the only graphene oxide modified classic carbon electrode and cobalt doped graphic carbon nitride modified classic carbon electrode and the graphene nanosheet modified classic carbon electrode and cobalt doped graphic carbon nitride at graphene nanosheet modified classic carbon electrode in phosphate buffer solution 0.1 molar pH 7. So we found that the maximum current we found at the final nanomaterial which we have prepared when we modify the classic carbon electrode. So further, we have studied with the different concentrations of the quinol, and we found that yes, there is a good electro-oxidation responses were recorded with the differential pulse voltammetry, and we found the two calibration curve. From the 2.5 nanomolar to 9 into 10 to the power minus 8 molar and 1 into 10 to the power minus 7 molar to 32 micromolar in phosphate buffer saline. So with this range, because the concentration current increases linearly with concentration, so that's why we have found two calibration plot 1 and 2 with the different ranges, but in the series. So for this study, we have optimized the conditions also. We have first studied the effect of pH, whether which pH we have to use for this kind of study. So we have recorded the response of the quinol in 0.1 molar phosphate buffer solution in pH 4, 5, 6, 7, and 8. And we have found the maximum current in pH 7. That's why we have done all the electrochemical study for the quinol in the pH 7. And further, we have also studied the amount of cobalt doped graphic carbon nitride, how much the cobalt doped graphic carbon nitride we have to utilize. So we have utilized the different amount of the cobalt doped graphic carbon nitride, and in this condition we found that when we take the 1.5 milligram per ml cobalt graphic carbon nitride, when we mix, then the maximum current we obtained. But when we increase the concentration, the current decreases. It may be due to the formation of the thick film thickness, or you can say the higher concentration of the graphic carbon nitride. As we know, the graphic carbon nitride is a little bit semiconductor. It behaves like a semiconductor, so current decreases. That's why we have taken the 1.5 milligram per ml. This we have optimized. Then we have checked the different.
3 minutes left.
Yes, sir. Different interferences which may be present in the sample, like resorcinol, catechol, citric acid, phenol, glucose, dopamine, magnesium chloride, sodium chloride. So we found that there is negligible effect of other interferences may be present in the system. Then we have done the cosmetic sample analysis, but we have taken some cream from the local market, and then we have done the standard addition method, and then we found the very good recovery results from with the percentage from 99.7 to 100.1. And then we have validated this result with the spectrophotometric determination, and we found that yes, there is a much compatibility between the two methods. And then we have compared our results with the already reported works. We found we have very much better results as compared to other previously reported works. Some works have been reported. So now I can conclude my work. A simple and efficient bio-nanocomposite was prepared through the electrochemical exfoliation of the graphite anode in the presence of amino acid L-cysteine, and further anchored with cobalt-doped graphite carbon nitride for the determination of Quinol, which is skin lightening agent, which is generally used in the skin creams and using differential pulse voltammetry. And here in the synergism between the graphene nanosheet and cobalt-doped graphene nitride enhances the catalytic power and promotes good electron mobility in layer-to-layer working as the arbitrator for transporting electron holes. Moreover, graphene largely allows the conveyance of carriers together in cobalt-doped graphite carbon nitride as it transport the holes also. So electrochemical sensing of Quinol was recorded in the two broad linear ranges with the detection limit 2.4 nanomolar. The 2.4 nanomolar is that concentration, which is the lowest concentration which can determine through our modified electrodes. This proposed sensor shows a good stability and high selectivity. So in the future, we can prepare this electrode as a sensor, for a good alternative for the real-time analysis of Quinol in cosmetics and other environmental samples. These are the references. And this work has been recently published in Talenta. And now I acknowledge organizing committee members for giving me this opportunity to present my work. And I also acknowledge UGC and CSIR for the financial assistance. And lastly, but not the least, to my research scholars who have done all this work. Thank you.
First of all, thank you very much for invitation. This is a very great pleasure to take up in this conference. And for environment protection, it is very important to make a monitoring of the environment. Only in this case, it is possible to use something for environment. And I will speak about extra sensitive environment sensor, new generation of environment bio-nanosensor. And in this, last keynote have spoken about bottom-up sensor, and I will speak about a sensor based of bottom-up bio-nanosensor. This bio-nanosensor are based on shape memory alloy, special smart material with shape memory effect. You see this such shape memory alloy, and sorry, I cannot make next slide. So then I will present in this way. And in this is something like bimetallic plate, what you see, but this is 1,000 miles stronger and for deformation. Why? Because this is shape memory alloy with very great deformation because of phase transition, and such shape memory alloy give possibility for very great miniaturization. And using this shape memory alloy, what was not so used because of problem, because they need training before use and have fatigue effect and long response time. And our laboratory have solved all this problem. And this new composite, exactly composite, like is this conference, can be treated by standard technologies. And you see this video, this is shape memory alloy. And the table is room temp is high temperature, and room temperature is air. And only by this small change of temperature, they make such a beautiful dance. And this is connected with, you see that this is very quickly changing. This is a very small untoward time. And this shape memory alloy, this is something like material from movie Terminator 2. And you see, this is also water is hot, and only by small small movement of by small distance from this water, there is a large movement. And from this shape memory alloy, we should like to make actuation. And this is actuator by what, and this actuator is very good in use very quickly. I try to show you. This is nearly by 200 gigahertz. And this 200 gigahertz is one of records in the world very, very quickly. And unfortunately, video we cannot see. And what is this? For what this can be used? This can be used for bottom-up nano-assembling from individual nano-device for environment. There is a lot of nanomaterial, nanotubes, nanowires, and from such nanowires it is possible to make special nano devices different. For example, this is nano laser or the nano diode. This is only cross section of two indium phosphor nanowire, and this is building block for future nano devices. And such future nano devices, this is bottom-up nano-assembling, like it was in last keynote. This is chemistry, and this is mechanical. And such mechanical can be used for producing of nano devices. And such nano gripper can pick up and place, cast, cut, pull, bend, turn object from the size 1 micron to 1 nanometer. This nano gripper is placed on the end of the nano position effect, like nano manipulator, and it actuated by laser heat or by some other possible, for example, electric current, or maybe in future by magnetic field. And we see that this is possible to actuate this nano tweezer. And this nano tweezer, we see, this is overview of the system, and this is nano tweezer. And what we are doing, this usually top-down nanolithography is very expensive and very complicated. And we offer to take individual nano object, for example, this or some other, and make bottom-up mechanical assembling for nano devices. Current nano assembling is not have not very good security because they are based on liquid technologies. And we offer make nano devices instead of top-down lithography using this nano gripper. What take individual nano object. Here we see that it takes zinc or nanowire, and after this, cut this, bring on the substrate, fabricate individual nano devices. And because we can manipulate only what we can see. And now I'm not sure. And what we see, this is handling of tip of the sealer on the leg of mosquito sensilla, this is hair on the leg of mosquito. And this is our gripper. This take special hair on the leg of mosquito, take, and this bring, this can, after this, make with this part of hair like everything what it can. This is also possible to make with carbon nanotubes and and make different devices. For example, this is a suspended ring, and we use this nano gripper for handling of carbon nanotubes. For example, here is in ion beam. This I don't know why they don't show videos, but I show photos about this video. This is nano gripper. This take nano bundle of nanotube and bring this to substrate. Or for example, take a whisker or take graphene. And this is possible to pick up, to disconnect from forest and bring to the substrate. And after this, it is possible to make special individual nano device. In this case, this will be possible to make bio-nanosensor with record sensitivity. I don't know why I have so many beautiful videos. This video, it is not possible to show. But in every case, for example, biomedical and sensor, bio-nanosensor is not possible to make using standard top-down lithography. This we see carbon nanotubes is a main element of such bio-nanosensor, and we see that this is not planar. And this nanotube can be make special functionalization of this, and after this, this can be extreme sensitive for shadow special environment not friendly component. And this will be done. This will be done with record sensitivity, femtomolar sensitivity. So we can feel nearly by one molecule with very great sensitivity. And now I show how this is possible to make this. This is nano tweezer, and this is, for example, some nanowires. Nano tweezer takes some nanowires. After this, it must be placed on the contact for making special individual nanosensor based of individual nanowire. This is bringing to contact. This is trying to place on the contact. But there is not only one, there is some more. This is placing on the contact. This is overview of this. This is going of this process. This is not correct placing of this nanowire. This is trying. This is not so simple effect. But at the end, we have nanowire placed on the electrode, and based of this, it is possible to make a special environment, a bio-nanosensor with record femtomolar sensitivity. Here we see something, for example, in the phosphor nanostructure. And this is field effect transistor. When some not good, not so good stuff material from environment come to this sensor, then it change functionalization of the sensor because of absorption, and after this field effect transistor show changing in a volt ampere characteristic, and we see that this changing is exists. And by this way, we can say if volt ampere characteristic of this nano FET transistor don't change, that there is no bad material in the air, and if or in water, in environment, and if changing there is, then there is some bad for environment material. And by this way, this is especially new technology and new type of sensor for environment. And this is possible to make this such sensor, many of the sensor very quickly, because we have seen that this can be working, nano gripper can be working very quickly, and also this is possible to working in parallel. Then I come to conclusion. New composite shape memory material allow creating record small and record fast micro nano tools. Composite nano tweezer approved to make manipulation of nano object. The new nano manipulation system opened up horizon for frontier nano-assembling of bio-nanosensor for environment. And this nano tweezer can be actuated with frequency from 1 kilohertz and also up to 1,000 kilohertz. So thank you for attention.
Yeah, thank you.
My name is Dr. Sayantan Guha. I'm currently appointed as an assistant professor at the Center for Data Science, Shiksha Anusandhan University, Bhubaneswar, and I'm grateful to be offered this opportunity by ICCMEPR Conference Committee to invite me to deliver this talk. So this is my title, Log Wave Propagation in Layered Piezoelectric Structures for Sensor-Based Applications. So these are the contents of my presentation, which I'll cover separately. Firstly, before going into the topic, let me give a brief overview of what piezoelectric materials are. They are a special type of material that can convert electrical energy to mechanical energy and vice versa. This property was discovered by the Curie brothers. And owing to this energy conversion property, they have been used for many years in several different branches of science and engineering in applications that involve sensors, actuators, transducers, and so on. Let me give you some examples among infinite examples out there. So here's a realistic example. There's a company called Innovatech in Israel. What they have done is they have installed these piezoelectric patches throughout their country's railways. Now, when a train passes over a track, it creates a huge amount of stress. That stress is converted to electrical energy by these piezoelectric patches, and that electrical energy is stored in underground cells for later use. For example, for switching on the lights along the railway tracks. So essentially, we are getting free energy. Here we see a club in France that have installed piezoelectric patches in the floors. So when people are walking or running over it, so they are creating mechanical stress that is converted to electrical energy, which is used to switch on these lights. There are several other applications. Here we see an ultrasound transducer that employs piezoelectric materials. Then we have sensors, other types of transducers. They are in your phones, watches, lighters, and so on. So you can see it's a very versatile object. But the motive of this work is focused on one specific application that deals with SAW devices or love wave sensors, specifically these love wave sensors over here. So what it is a guiding layer, this green layer over here. This lies above a substrate, which I've colored in black. And on top of the guiding layer, there are two IDTs, one input IDT, one output IDT. They are lined with piezoelectric materials. So when we apply an RF signal to the input IDT, it creates different types of waves called love waves, which propagate along this area and reach the output IDT, where they are transformed to a measurable electrical signal. Now, the interaction between this wave and the propagation medium of the guiding layer causes a sensing region, which I've called over here as the sensing area. And the difference between the properties of this guiding layer and the substrate entraps the love wave along this area and thus increases the sensitivity of this entire structure. So our main motive is to find out an optimal solution for the compositions of the guiding layer and the substrate, which lowers the phase velocity, thus increasing the sensitivity of the device. And here we see some particular examples of SAW devices. It can be used to monitor water quality, monitor air quality, and so on. Let me quickly explain how. So initially, when there is no contaminated water placed on the SAW device, we know the velocity of the wave. Now, when the contaminated water is placed on the SAW device, the contaminants bind with the sensing region and they alter the phase velocity. When we find out the difference between the phase velocities of the altered stage and the unaltered stage, then we can correlate this thing with the contaminant concentration and we can find out the existence of the impurities present in the water. Similar techniques for the air contaminants. And this SAW device is very affordable, energy efficient, and highly sensitive, for which it is used in many branches of science and engineering. Now that the application part is done, let us focus on the mathematics behind it. So here I have a piezoelectric layer and it is lying above a piezoelectric half space. Here we have the x-axis, here we have the y-axis. Now since the log wave is propagating along the x direction, it is antiplane in nature. So the displacements are given by u equal to 0, v equal to 0, and w, which is a function of x, y, and t. Similarly, phi denotes the electric potential. It is also a function of x, y, and t. Now we start essentially with the problem. So we have some standard equations which are given by equations 1 to 5. And they are the equations of linearized coupled piezoelectricity without the effects of body and electric forces. Now, as per the undertaken geometry of the problem, these equations result in equations 6 and 7, which are coupled PDEs that we need to solve. Now, in order to solve this problem, we are going to take two different sets of boundary conditions. The first one is the electrically short case. The second one is the electrically open case. And we are going to have 6 different conditions for each case. For the electrically short case, at the free surface that you see over here, we have mechanical stress is 0 and electrical flux is 0. And at the interface of the layer and the half space, there are 4 conditions which are all continuous. So the stress, mechanical displacement, electric flux, and electric displacement are all continuous along this surface. Now for the electrically open case, although the stress is 0, since we are considering the open case, electric displacement is assumed to be 0 over here, and the continuity conditions remain the same. So you see, we have 6 different boundary conditions. I'm going to explain now why we have 6 boundary conditions. So in order to solve the 2 equations which are shown earlier, the coupled PDEs, we assume a solution form given by 20. And on applying the solution form on those 2 equations, we obtain the mechanical displacement and electric potential of the layer given by equations 21 and 22, and the mechanical displacement and electric potential of the half space given by equations 23 and 24. You can see in equations 21 to 24, A1, A2, A3, A4, A5, and A6 are unknown constants. Since we are dealing with 6 unknown constants, we are going to need 6 equations to solve them. That is why I showed 6 different boundary conditions. Now, on applying the different boundary conditions, we finally get the dispersion relations, which we are going to solve the problem with. So here we focus on the last part of the presentation, the results and discussion section. So what I've done is I have considered 2 different types of half spaces. One's composed of B80IO3, the other time composed of PZT7A. Now, when the half space is composed of B80IO3, I have taken these different materials for the layer individually. For example, one configuration can be PZT5A layer with B80IO3 half space. Then we can have PZT4 layer with B80IO3 half space, and so on. And the data of all of these materials are available in references 2 to 8. So let us focus on the problem at hand. In figure 2, parts A and B, I have shown the dispersion relation for the electrically short case for 2 different configurations. Let us focus on A. We can see as the dimensionless wave number is increasing, the dimensionless phase velocity is decreasing in magnitude. And our entire objective is to find out that configuration which lowers the phase velocity the most, because least phase velocity implies greatest sensitivity of the device. So it can be seen for each and every mode that when the layer is composed of PZT5A and the half space is composed of B80IO3, the black curve has the least magnitude. That denotes the PZT5A layer. And gradually, the magnitude keeps increasing for PZT4, PZT5H, PZT2, PZT7, and CDAC. So it can be concluded that if the layer is composed of PZT5A and the half space is composed of B80IO3, then that SAW device is going to give us the most enhanced performance compared to all other combinations in this field. Similarly, in figure B, we can see if the half space is composed of PZT7A and the layer is composed of KNL and TS, then the phase velocity magnitude is the least, and it gradually keeps increasing for KN into 2, BNK LBT, and PZN 4.5% PT. So if we consider a PZT-7A half space along with a KNL and TS layer, then the phase velocity is the least, which ensures that the SOR device composed with these combinations is going to have the greatest performance among all these 4 combinations. So here we go to the last graph of this presentation. Once again, I have composed a SAW device with a BATIO3 half space followed by 6 different types of individual layers. And these 3 figures, A, B, and C, are corresponding to the electrically open case. For the first case, we see that for lower values of wave numbers, the phase velocity magnitude is the least for CTSE, followed by PZT7, followed by PZT2. So it can be seen that the phase velocity is least for CTSE. But when we go for higher wave numbers, we see that the phase velocity is least for PZT5H, followed by PZT4, and then by PZT5A. So if I compare the contents of figures A and B, we can see that overall, for all wave numbers, the phase velocity is composed of CTSE and the half space is composed of BATIO3 for the electrically open case, which implies that the CTSE BATIO3 combination for the electrically open case is going to be more suitable for a SAW device. Lastly, for the PZT7A half space, I've considered these 4 different types of layers, and it can be seen that the combination KNL and TS along with PZT7A gives us the least phase velocity, followed by KNNT2, BNKLPT, and PZN 4.5% PT, which gives us the highest phase velocity. So over here, we can conclude that if the SAW device is composed of KNL and TS with PZT7A, then the phase velocity is the least, and that device is going to give us the most enhanced performance compared to all other structures. Now, a question can come to mind, which I haven't covered previously. How did I choose these combinations? Indeed, I can take any other combinations, but there is a restriction in mathematically speaking. So let me just quickly say it. We know a love wave propagates in a medium whenever a low velocity layer lies over a high velocity layer, and the velocity of the love wave lies between these 2 velocities. So mathematically, velocity of the layer has to be less than velocity of the love wave, which has to be less than velocity of the half space. So when I chose these combinations, I found out the velocities of each and every layers. I found out the velocity of the half space, and I ensured CL is less than CH. After that, I was able to solve the entire problem. You can take any other combination, but always keep in mind CL less than C less than CH combination has to be satisfied. Otherwise, love wave is not going to propagate. Now, with a final note, let me conclude. Is this the end of this research? No, it's not. So I can replace these piezoelectric materials by several other different materials. For example, recent times have shown us that there are piezoelectric fiber reinforced composites, which are composed of 2 or 3 different types of materials. And using those materials, maybe we can enhance the performance of SAW devices even further. That being said, it is an open domain. Anyone can solve those problems. I have also solved some problems over there. And that concludes the presentation. These are the points of conclusion, which I have already covered. So I'm not going to go through them again. So I'm grateful to Shiksha Anusandhan University for providing me the best facility to carry out this research work. And I'm also grateful to the Conference Committee of ICCMEPR 2024 for inviting me to deliver this talk. These are some of the references that I've used. You can go through them later on. Thank you everyone for your time.
Okay. Good afternoon to all the speaker and delegates and the faculty members present here. Myself, Dr. Indranil Maity. I am currently working as an assistant professor in Department of Electronics and Communication Engineering Department in Institute of Engineering and Management, West Bengal, Kolkata. First of all, I would like to thank ICCMEPR organizing committee member for inviting me in this session. Today, I am going to present my work having titled A Comparative Study on Formaldehyde Detection Capabilities Between 2 Different Sensing Materials. The first one is a Pristine graphene, and the second one is a silver doped graphene sheet. The present papers is authored by myself, Indranil Maity, Shoubik Bhanjo, Shaubarno Chatterjee, having the paper ID of 057. The following index is basically consists of introduction, computational methodology, the results and discussion based on frontier molecular orbital, ESP, density of states, adsorption energy, binding distance, Mulliken charge analysis, and finally the conclusion, acknowledgement and references. So first of all, what do you mean by formaldehyde detection, and what is the importance of formaldehyde detection? Formaldehyde is basically a one type of vapor having different application in industry like resin, fungicide, germicide. Along with that, the higher concentration of formaldehyde detection is important because it can cause myeloid leukemia and other cancers. So here the target was basically the effective detection of formaldehyde via two approaches consist of sensing material. One is pristine graphene and the second one is silver dope graphene. And the results are basically based on DFT-based computations having HOMO, highest occupied molecular orbital, LUMO, lowest unoccupied molecular orbital, ESP, electrostatic potential, density of states, molecular charge, adsorption energy, and finding the binding distance. So the software tools which have been used, basically Gaussian 09W for the calculation purpose, Gauss View 6.0 is basically for the visualization purpose, and the density of states spectrum was plotted using Gauss sum 3.0 software. And the case 1 is basically denoting formaldehyde adsorb pristine graphene sheet, short form is PG, and the second one is case 2 formaldehyde adsorb silver dope graphene sheet. The short form is AG-G, that is a silver dope graphene. So two different structures have been considered. In the right side, the first figure is basically representing the pristine graphene sheet, and the second one, the bottom one, is basically representing silver dope graphene sheet. Here, carbon vacancy was considered in the second case, and over which the foreign atom silver was placed. And after optimization, these two structures have been developed, and the structure is basically having the carbon atoms, hydrogen atoms, and in the case of silver dope graphene sheet, the silver atom. And as I already mentioned the name of the software, along with that, the simulation process was carried out basically PB functional, along with the basis set of 3 to 1G. And the adsorption energy, which is crucial for the sensing application, the how much adsorption probability to find out, basically evaluated with the help of this formula. And coming to the first result based on the FMO, that is frontier molecular orbital, which is basically highest occupied molecular orbital and the lowest unoccupied molecular orbital. Here, the three-dimensional molecular orbitals have been plotted, where HOMO denotes the electron donating probability and LUMO denotes the electron accepting probability. And in the figure, the red colored zone representing the positive regions and the green colored zone representing the negative region. What do we mean by positive and negative region? When the wave functions are overlapping, either they may be get it additive in nature, or maybe the constructive interference kind of things, or the destructive interference kind of thing. So depending on the wave function, the HOMO and LUMO plots have been represented, where the bottom one is basically the HOMO and the upper one is basically the LUMO. In the case of pristine graphene, as the total number of electron into the system is 210, which is even in number, so therefore the restricted functional was used, and here we have got the alpha orbital, and the LUMO minus HOMO gap, or E HOMO LUMO gap, is basically was found out as 1.33 electron volt in the case of pristine graphene, as shown in the right side of the figure. In the second case, where silver dope graphene has been considered, here it has been observed that as the total number of electron is 251, which is odd in number, so unrestricted functional was used, which gives alpha orbital as well as beta orbital, where alpha orbital denotes the upspin category and the beta orbital denotes the downspin category. And here the band gap was found to be in the case of LUMO and HOMO. The gap between LUMO and HOMO in the case of alpha orbital is basically 0.27 electron volt. And in the right side, which is basically denoting the beta molecular orbital, here the band gap was basically 0.89 electron volt. So now coming to the electrostatic potential, here the upper figure denoting the pristine graphene and the bottom one denoting the silver dope graphene. Here the red color, the red color representing the lesser electrostatic potential, which denotes higher number of electrons. The green region representing the neutral zone or the neutral region, and the blue region or the cyan color representing higher electrostatic potential or less number of electrons. As a result, the blue region or the cyan color region representing nucleophilic attack. As we know, nucleophile means the electron rich and electrophile means electron deficient. So therefore, the blue region where the number of electrons are less in number, so nucleophilic attack will be occurred at that place. And in the case of red color zone, where the electrophilic attack will occur, and this electrostatic potential clearly means denoting the region where both the attacks will occur depending on the position of atoms or molecules and bonds. Now coming to the density of states, as we know, the density of states, basically the number of states available at a specific energy level. Here, these two plots, the first one is the PG, that is pristine graphene, and the second one is silver dope graphene. Here, the dots representing the nature of these two sensing material, where it was being observed that in the case of case 2, that is the bottom one, the height of the maximum peaks are reduced. So it denotes more number of electron transition from the lower level to the higher level. As a result, it can also be inferred that the gap between home volume is also decreased. So it is the second observation. And from the dots, it can be observed that as the conduction band minimum and the valence band maximum are overlapping, so they are semi-metallic in nature. Even in the case of graphene, we also know that in the Dirac point where the conduction band minimum and the valence band maximum merge together, so this point is also denoting the semi-metallic tendency. The Mulliken charge analysis have also been calculated individually for the atoms. Here, some of the ellipses are showing. It can also be observed that, suppose here in the case 2 is basically the silver dope graphene, and here the oxygen O46, the same oxygen atom denoting the charge of 0 minus 0.348 in the case of pristine graphene, and in the case of silver dope graphene, it is 0.365. So the charge transfer probability or the charge transfer value is also updated or modified in the presence of silver atoms. So all the atoms are having different charges in the presence of pristine case and the silver dope case. And here the yellow marked region, if you compare the left side with the right side, you can see that in the case of suppose C20 and C12, the values are positive in nature, but in the case of case 2, the same two values are in negative, whereas in the case of the green one, the initial value in the case of pristine graphene is negative in nature, but here it is basically positive in nature. So all the charges are modified. Now coming to the important point of view in the case of sensing application, the adsorption energy and the binding distance. What do you mean by adsorption energy? Adsorption energy denotes the probability of adsorption of a gas or whatever the molecule into the sensing material. Here, the higher negative value denoting the greater probability of adsorption. From the table, it can be observed that these upper three rows denoting the calculation of the energies, and the bottom two rows representing the adsorption energy and the binding distance value. So in the case of case 1, that is the pristine graphene, and in the case of case 2, that is the silver dope graphene, the binding distance is also reduced. Suppose in the case of case 1, it is 3.14, but here in case 2, it is 2.2. So the binding distance is getting lower or smaller in amount compared to the earlier case, which denotes the higher tendency to bind in the case of silver dope graphene. As a result, the adsorption probability is increased, so the energy is also significantly updated or enhanced compared to case 1 case. So it denotes the adsorption probability of formaldehyde in the case of silver dope graphene is higher compared to the pristine counterpart. So in conclusion, the band gap for the case of HOMO-LUMO plot was found to be lesser in case 2, that is silver dope graphene, compared to the case 1. And the magnitude of adsorption is significantly improved in the case of case 2, that is 154 times. And the binding distance, as I already mentioned, it is reduced compared to 3.14. Currently, it is 2.2, so 1.43 times reduction. And finally, we can conclude that if the material doped with foreign atom or silver nanoparticles, so the silver decorated graphene will be an effective sensing material for the detection of formaldehyde, and it can be useful for the case of gas sensing application or vapor sensing application. So I want to acknowledge Department of ECIM Kolkata, along with the Indranil Maity Department of IIT Bombay, and my project students and mentees. This is our group photo, and these are the references. And finally, thank you.